10 grams of steam at the boiling point are combined with 50 grams of ice at the freezing point. What is the final temperature of the system? Assume an insulated system. All right, so steam, we mean the water vapor or gas. I'm going to call the 10 kilograms the mass of our steam. I'll go ahead and put it into, 10 grams, I'll put it into kilograms. Mass of ice, 0.5 kilograms. So the steam is at the boiling point, meaning it is initially 100 degrees Celsius. The ice is initially, so ice initial, TII, is at the freezing point, so 0 degrees Celsius. Since we are assuming an insulated system, this is what we would consider a calorimetry problem, meaning if we add the steam energy that is removed and goes into the ice, all of that energy will add up to be 0, meaning there's no energy exchange with the surroundings. So all the energy this steam essentially gives away, that it loses, goes into the ice. And so they're just exchanging this heat energy between each other. All right, so the steam, it's, as we take energy out of the steam, it is going to condense. It's going to change phase from the gas to a liquid phase. So the steam, we have to account for this change of phase of the steam. Now, if you remember, change of phase, our equation is written as plus or minus m times L. I am choosing the minus because I need to take energy away or out of the steam, away from the steam, in order for it to go from a gas phase to a liquid phase. So the minus sign, I'm accounting for the energy needing to come out. I'll take the mass of the steam times the latent heat of vaporization, because the L sub V is the value we use between the liquid and gas state. But even once we have taken this energy out, this leaves us with liquid water at 100 degrees Celsius. So the equation m times L accounts only for the energy needed in terms of changing the phase. Whether we put the energy in or take it out, it's only for the change of phase and not the change in temperature. So we do need to account for any temperature change. In temperature, we have MC delta T. So the mass of the steam, it's liquid water now, so we just need C of water. And then delta T, we mean the T final the system comes to, which we're looking for, minus T initial of the steam specifically, because we're talking about the steam, the gas that's now liquid. So this is now the cooling of the water that was steam. So the T initial for the steam was 100 degrees Celsius. All right, so steam has two different Q values we need to account for. We need to change the phase, so how much energy is needed to go from a gas to a liquid state, and then the energy needed to take it from that boiling temperature down to whatever final temperature it will reach. Similarly, the ice, we have ice, so solid, at the freezing point. So we need to account for the energy needed to melt the ice. So the mass of the ice times the latent heat of fusion, because L sub F is for the solid to liquid phase change. But once this ice is melted, it's going to be at 0 degrees Celsius still. M times L is only the amount of energy that is going into changing phase. It is not any energy going into changing temperature. So we have to account for the change in temperature. So I'm using the MC delta T again to account for now this increasing temperature of what was ice. What was ice to begin with, but is liquid because of this term we accounted for melting. There's no other materials in the system, and so all of these Q's have to add up to be 0. That means there's just no energy exchange between the system and its surroundings. It's all within the system itself. So we're looking for the final temperature. From the test notes, we have C of water is 4190 joules per kilogram Kelvin. L sub F, 3.33 times 10 to the 5th joules per kilogram. L sub V, 22.6 times 10 to the 5th joules per kilogram. We're given the masses, we're giving temperatures. Now, whether we solve completely symbolically from here or plug in numbers, doesn't matter. This setup as it is right now is considered our symbolic equation. I sometimes find it easier to plug in my numbers now, though you don't need to. But I like to make sure I have the right temperatures attributed to the right material. So my first term was steam, that just needed the latent heat of fusion. Now this second term is going to be negative, but the negative sign comes because of the delta T. T final is this final temperature of the system that we're looking for. T initial is 100 degrees Celsius. So T final being smaller than 100, this term would end up to be negative. So I don't need to put a negative sign on it like I did on the first term. I did need that first negative sign. So for our ice, mass of the ice, C of water. Again, T final is what we're looking for. T initial is 0 for ice. So the steam and the ice have different initial temperatures. So our equation right now we have negative 22,600 for the first term. This I will need to factor through. So I'll have to multiply it first by the T final. So I get 41.9 T final minus 41,900 when I multiply it through to the 100. So that's this term. Oh, that one's 0, that's nice. 90. So plus 209.5 T final. So I'm going to combine my T final terms. And then my other terms. Which of course I can just bring that over in the first place. So we have enough here to solve for T final. I'm getting one that does not make sense. Okay, so let me go through my math again. All right, so going through here, it doesn't make sense because I'm getting an answer of 100 and something, which would imply the system got hotter, which is not going to happen. I put too many zeros in this term over here. This should just be minus 4190. So that's going to change this term. I'm getting 101.40. There we go. That makes more sense. Now my units on this are degrees Celsius because my initials that I plugged in were in Celsius. The difference in Celsius is the same as the difference in Kelvin. So by leaving my initial T's in Celsius, my final T is also in Celsius. Now, one other side note, it is common, well, actually, let me write it over here. Calorimetry is when we're saying all of the energy exchange is happening within the system. Because the steam is hotter, the ice is colder, they're going to exchange energy, the steam will cool off, condense and cool off, while the ice will melt and warm up. It is common to say that the energy the ice absorbs is going to equal the energy the steam gives off. Which that's true in terms of the absolute values. That's totally true. But in terms of our equations, especially when we're dealing with our delta T, we have to be careful with the signs. If you want to set a problem up this way, that's fine. But because the steam is giving off energy, you would want to write Q of the ice as the opposite, the negative of Q of the steam. And that naturally comes from where we started, this calorimetry. So the signs can, if we miss that one sign and just said Q of the ice comes from Q of the steam, just equated them in the first place, we would not get a reasonable answer, right? A correct answer. So just be careful with your signs.